Good morning, everyone. I hope you had fun yesterday in the laboratory. I just wanted to let you know that I think the results went very well, and we're going to analyze the data all together today. I'm not going to do all the work, right? You have to finish the work later for your own report, but I'll help you. And this is the result. So here you have the values of the maximum stress for the group in the morning, here in the middle at noon, and in the afternoon. Is there anyone from the group of 500 psi from 9 a.m. here? Yes? What was your maximum stress?
We didn't finish the test because it wasn't working.
So you couldn't run it?
No, it wasn't running when we tried it.
Or what's the problem with the pump?
Yeah.
The pump was, the pressure was going up very quickly?
We don't really know. It's probably the valve.
Okay. No, I think I know what it was. Yeah, that was not your fault. So don't worry about that, okay? So I'll talk to Gabriel, to Javier, to make sure that we give you a data set to work with. But don't worry, because we had two other groups to repeat that test, and the results were very close. So this is the summary, and Javier, will email you this table too, where again, these are the pressures that we set. This is the confining pressure or the radial stress if we were to, let me see if I can draw in here. I think I can. If we were to look at this sample, I'm not drawing the membrane here, okay? But here you have the radial stress, and on the axial direction we have the axial stress. Okay. The radial stress is something that we prescribe, that we set the value and we keep it constant. The axial stress is the maximum value that we measure. And remember that as we start loading, that load increases, and we are just putting the value of the maximum value. Something we didn't say in this test, but I'm going to tell you now, is that the pore pressure was around 0 because the rock was dry. And what that means is that even if we compress a rock, because the compressibility of air is very high, the pore pressure would not change within the rock. But if you have that filled, say, with water, and you start to compress it, then the water will compress too, and the pore pressure might increase. So let's not get into that right now. But in this case, the pore pressure was 0. And because of that, the total stress and the axial stress are going to be the same. And something else that we're going to introduce now is the deviatoric stress, which is the difference between the maximum principal stress and the minimum principal stress. So in this case, let me do it. I'm going to do it with another color here. The deviatoric stress, usually we call it with sigma subscript d, is going to be sigma 1 minus sigma 3 and in our particular case is the axial stress minus the radial stress. All right, so that value is just the axial stress minus the radial stress. We are not using it here, but in the next example we'll see what that is. So the only thing I did here was just to plot the maximum stress, sigma 1, which is in this case column D in the y-axis, and on the x-axis sigma 3, which is the radial stress. And these are all the tests that you did in the laboratory. 100 psi, 300 psi, and 500 psi. And you see that the data is more or less, I would say it's pretty good. Considering the variability of the rock, the values are quite repeatable. So different groups working on different load frames and slightly different samples from the same block, they gave more or less the same result. And what this equation tells you is that what is going to be the unconfined compression strength predicted by this equation. That will be the intercept of this line here at x or sigma 3 equal to 0, right? And that's going to be this value. And what we have here is that this equation is telling us the extrapolated unconfined compression strength is 4,515 psi. And the parameter, the friction parameter Q is 10.3. If you wanted, and you have to do this for your report, if you wanted to compute the cohesive strength and the friction angle, what you have to do is you have to use these equations. Okay, so from this equation, if you know what UCS is, then the cohesive strength will be UCS divided by 2 divided square root of this parameter Q, which is 10 point something, right? And if you wanted to get the friction angle, the equation is somewhere over here. Let me see. I think I forgot to write it. But
Just use that 4.4, right? Equation
4.4. Well, the thing is 4.4. It's easy to calculate Q as a function of the friction angle, but it's not. You have to do some math in order to get friction angle as a function of Q, which is not too difficult, right? But I had done it somewhere, but I think I didn't write it here. So I will add it later on. I'm pretty sure it's in my notes somewhere over here. But you can work on the math and you can do it. It's not too complicated. But I have done it somewhere already for you. It's just that it's not here. Well, I found it, don't worry. But there is another equation that can tell you what is friction angle as a function of Q. And with these equations, then you can go now from this space to that space. And this is exactly what you have to do for problem number 1 of the homework. For problem number 1, now you have data for another type of rock. In this case, this is an unconsolidated, uncemented sand from the Gulf of Mexico. It's actually real sand that we tested here in the laboratory. There is quite a bit of gas and oil produced today from this sand. And here you have the values of confining pressure. The pore pressure is 0, the same as in the experiments that you did in the laboratory. And here you have the value of peak deviatoric stress given in this column. So let me tell you what's the difference now with what you did in the laboratory. All right, so let's come back very quickly to the laboratory. In the laboratory, we measured sigma A or sigma 1. And that was because we measured it outside the triaxial cell. So let me do a schematic very quickly. Your triaxial cell looks more or less like this. that's a pressure vessel, and here you have a steel piston that goes inside and pushes on the rock. The rock is somewhere over here, and we have a bottom end cap and a top end cap, but now this top end cap I'm going to put something else here, but it's just the same. It's in contact with the rock, and then all of this is isolated with a membrane. Okay, so in the laboratory then we apply a confining pressure that goes in all directions, even pushes the rock from the bottom to the top, and that's the confining pressure, or also the radial stress. If in the lab we measure what is the force that you need to apply in order to fail the rock, then that's going to give you the total axial stress, which is going to be equal to the force divided by the area of the sample, which in this case is also the area of this piston. But force divided by the area of the sample, then that will give you the axial stress. So in the laboratory then, here, let me call it the one that you did. What you measure are sigma r, or that you prescribe sigma r, and then you measure sigma a. In some other tests, which are a little bit more precise, you do something slightly different. You don't measure the force outside the triaxial vessel, but you measure it inside. And when you measure that force inside, then what you measure is going to be not the actual force. It's not going to be the total force, but it's going to be the difference between the radial stress and the axial stress. I did a minor mistake here, so let me fix it, because I need to get this load cell outside here. Okay, so very similar to what we had before, but the load cell is going to be here. Let me see. It's going to be right there. So when that's the case, if you have the load cell and you increase the confining pressure, it's not going to measure anything because it's feeling the load cell is feeling the pressure from everywhere, from here, from there, and from everywhere. And these load cells are not designed to measure the confining pressure. They're rather designed to measure a force when you deform or when you apply a force in axial direction. So even if you increase the confining pressure, they are not going to react, and they're not going to show any measurement. It's only when you start to apply an extra stress on the rock when you start to measure a reading. And because of that, in this case, these load cells, as you would do in most research labs, like for example, across the hallway of the undergrad geomechanics lab, that's my laboratory, and in there we have something very similar. There we measure sigma r, or the confining pressure, but then we don't measure the total axial stress. We measure the difference between these two, or the deviatoric stress. And that's going to come from the reading of the load cell inside the pressure vessel. And that's a lot more precise than measuring it outside. And that's exactly what you have over here, because these measurements we did it in that laboratory. You have the peak deviatoric stress and not just the axial stress. And there is one more thing that you have to notice over here, and it's that now we make a difference between total stress and effective stress. In this case, still they are the same because pore pressure is 0. But remember that in the laboratory, in general, you're going to measure total stresses. And we'll see this just in a sec, okay? So if you wanted to compute what is the total stress S1, what would you do in this case? This is S1 minus S3, and you want to make a plot S1 versus S3, right? Confining pressure is going to be directly the minimum principal stress, and if you want S1, what do you do?
The last one, the first one.
Exactly, you just do that, right? So in this case, in general, when we're dealing with total stresses, if the deviatoric stress now in total stresses is S1 minus S3, then S1 is just going to be SD, the measure value, plus S3. And in terms of what we actually measure, then this is the deviatoric stress plus the confining pressure. So you have everything in here. You have the confining pressure, you have deviatoric stress, then you just have to calculate S1, and this is going to be directly S3, and you're going to be able to do what we just did over here. It's going to be exactly the same. From there, you calculate what is going to be the friction angle and your unconfined compressive strength, which should be close to 0. Don't put a negative value, okay? Even if your fitting gives you something a negative value, that doesn't make sense. It should be either 0 or something slightly bigger than 0. Yes?
For the lab, do we need to make that plot you just showed, or a plot of the more circles?
Well, in here, for homework number 1, you have to do the 2 of them. Yes. So I would suggest that probably work on homework number 1 first, and then use the same spreadsheet, and then do also the problem for the laboratory. The homework? Well, we need to talk about that just in a sec, because there's some small thing that may change the plans. One warning about this. More circles. I don't know how to plot more circles with Excel. I don't know if anyone of you knows how to do that. You know?
I was going to do it more in like a rudimentary sense, just making like a shape and then matching it with the sigma 3 and the sigma 1.
Okay, that's one solution. The other thing you could do, and that would be valid either for Excel or if you do in Python or MATLAB, is just with the center of the circle and the radius of the circle, then you can create an array of values going from 0 to 180 degrees and plot just a component x and y. You could do that.
Can you just plot half the circle?
Yeah, half the circle is fine. But again, you're going to have to, in order to plot a circle, you're going to have to plot several values in order to get a circle shape. All right? All right, so now that most of you are around, people that arrived a little bit late, I received a request about moving the exam after spring break. How do you guys feel about that? Everyone agrees with it? Well, let me tell you something before. You know, even if the majority wants that, I'm not going to move it if a minority says no, because we agreed on this a long time ago, and everyone should have, planned in advance. So even if minority says like no, then I'm not going to move it. But so again, let me ask you. Raise your hand if you want to move the exam after.
Tuesday after spring break or the Thursday after spring break? Or
This is the same for me. So let me tell you the problem is after spring break you're gonna forget a lot of things. You're gonna have you're not gonna feel in the mood of studying. To me it's better that you do it like you do it next week. It's not going to be too difficult. It's just going to be here in class, 1 hour and 10 minutes. So if you have been doing your homework, you will not find this challenging. Okay? So I don't want to put pressure on you in front of your classmates too. I'm going to send an email, and then you please reply to that email, okay? But what we need to decide is rather soon. And if we don't change the exam date, which is going to be Thursday next week, that means that the homework is going to be due Tuesday night. And this homework is very easy, don't worry. It's, what I showed you before. That's all what you have to do, and you have to repeat in problem number 1 and also in problem number 3. Problem number 2, actually you already know how to do it. It's just more of the calculation of Young modulus and Poisson ratio and things like that. Okay? So I'll send you an email right after class. Okay, so then think about that. Again, I think problem number 1 then is very easy. First, sigma 1 as a function of sigma 3. Then from there calculate UCS and this friction coefficient Q. And from there you plot the Mohr circles. And with your Mohr circles you plot the line tau equal to S0 plus sigma n times tangent of friction angle predicted by the previous problem. Don't try to do the fitting or the regression problem with the circles, because it's a lot more difficult. Just do it first with the data points. Yes?
Do you want us to do our calculations in matrix notation during the exam?
No. I mean, you have to understand the matrices, but then you have to be able to convert that to equations. If you want to do it in calculation in matrix notation, that's fine, but I'm not going to ask you to multiply a matrix times a matrix. Probably a matrix times a vector, that may be possible, but not a matrix times a matrix. Okay? Yeah?
Will we have an equation sheet for the exam?
I'm working on that equation sheet. My plan is to provide you an equation sheet, and well, I always provide an equation sheet, but this time I'm planning to make something a little bit better organized and similar to what you have for reservoir engineering, something like that. So that's my plan. But I will provide the equation sheet. Yes.
Are there any examples of exams provided or exams?
And I'm going to provide also all the exams for you to practice. Okay? All right. So this should be no problem, okay? Problem number 1. It's very easy, very similar to the one of the laboratory. It's just the data, it's coming in a slightly different format. All right. One more thing I wanted to do related to this, and just to close this topic about the laboratory, is that we also take a look at this and compare it with data from other rocks. So I converted this also to SI units, and here you see that the UCS for this rock is 31 megapascals, and the friction parameter is about 10. And here I have a summary of typical strength properties of rock, where these values at the origin, those will be the UCS, and the slope of these lines, those would be the friction parameter Q. So in our case, this Berea sandstone, we said that it has a UCS of about 30, so that would be somewhere over here, and we'll have a friction coefficient of about 10, which will be actually quite steep, steeper than most of these lines, so somewhere around here. And that falls on the end of a relatively weak rock. And you know, that Berea sandstone that you tested in the lab is relatively weak. There are some other rocks that are a lot stronger, like igneous rocks. And there may be also some sedimentary rocks that are a lot weaker. This one from the laboratory that you have over here, again, we said that it doesn't have any cohesive strength. So it's going to be a line that starts here at 0, and it has a relatively flat slope. So that's going to be quite weak. And in general, sedimentary rocks are weaker than metamorphic rocks and than igneous rocks. Now there is a lot of attention on igneous rocks because of geothermal activity and drilling in igneous rocks, and even doing fracturing in igneous rocks. All right, so let's continue with the homework. Actually, and now you have all the tools to solve the homework. The other topics that we have to see, let me show that. The other topics that we have to see are topics that we're just going to talk about them mostly in theory, but you're not going to do any problem related to those. So what you know by now, it should be enough to solve the homework. All right, problem number 2. Problem number 2 is a triaxial test that was done in the research laboratory, which is across the hallway. And you're going to have to download this file over here. And with this file, here you're going to have a triaxial test in which, let me copy it over here. We have to do what we have been doing to convert this into data in columns. So that looks good. So this is a lot of data, so don't try to do it manually. So first column is time, second column is confining pressure, third column is deviatoric stress, and then you have EX is the axial strain and EY is the radial strain. So this is axial strain and this is radial strain. And basically what you have to do is just to let's see what the problem says, but just you have to find the strength of this rock. So plot the deviatoric stress as a function of strain. That's going to allow you to calculate your Young modulus. Something important that also you have to calculate is what is the velocity of loading. That's what is called the strain rate. How much the deformation is changing with time. Then you have to compute a Young modulus for loading and a Young modulus for unloading for the two cycles actually. You have also to calculate a Poisson ratio, and the only new thing here is that you're going to have to compute a volumetric strain. So let me show you very quickly how that's going to look. Do you remember, guys, what is a volumetric strain? Yes, so it's a summation of all the strains, and because we're considering that the radial strain is going to be the same in two perpendicular directions, then we just multiply by 2. And what you're going to see is something like this. And notice the confining pressure in this test is 1500 psi, 3 times higher the one that you did in the laboratory. What's going on here? Wait a minute. Okay, apparently there was a problem with my data, so let me do this again. Okay, so I'm gonna put tab and space, both of those. Okay, I think now it's good. And this is PC, this is sigma D, EX, EY, and let me do this again. This is that plus 2 times this. Small mistake over there. All right, so I'm going to plot this very quickly. All right, so that's axial strain. Let me add radial strain here. Now that's with radial strain. And something else that you're going to take a look at here is what is also the value and how volumetric strain changes with loading. And that's the value of volumetric strain. I'm going to ask you to do something that I'm not going to do right here, and it's going to make your plots a lot easier to deal with. Please, when you do these plots, make these lines start at 0, all of them, over here. So in that way, all these 3 will start right here at x equal to 0 or strain equal to 0. So just basically 0 the strains at the beginning. And here, we see with loading, we see the loading, then you have to compute the Young modulus for that. We see 2 unloaded cycles, you have to compute that Young modulus as well. And the new thing from here is that you're going to have to also compute this volumetric strain curve. And this volumetric strain curve tells you when the rock starts to fail. When we compress a rock elastically, we added the compression, confining pressure, then we add the compression in the other direction, you expect always the rock to get smaller. And that makes sense, right? That's why this volumetric strain is every time more positive, which means more compression or more contraction. But however, notice that at around 80% of the maximum stress, the volumetric strain, instead of getting every time more positive, which means smaller, goes into the other direction. And what that means is that at that point, the rock is starting to dilate. It's starting to get bigger. In this region over here, it's not bigger than before, but is bigger with respect to the smallest size. But in this region over here, the rock is actually bigger than what it was before. And the reason for that is that when you get close to fracturing, some of your fractures may start to dilate as the grains have to go on top of each other. So imagine that, so this is your rock, and as the faces move on top of each other, they have to dilate, and that dilation makes the rock bigger. And if you were to make a zoom in the sand grains, you will see that, for example, if the sand grains are overlocked like this, and then one has to go on top of the other. Wait, let me make a zoom out to make it clearer. So if these are here and you need to move this over this one, my hands has to be further away in this direction to go on top of this grain. And as it goes on top of this grain, the fracture dilates, and this dilation is what it makes the rock get bigger. Since I have the camera on, remember that I'm asking you to provide a picture of your sample. And with that picture of your sample, I also want you to measure what these failure angles are, which is the angle between the plane of the maximum stress, which is this plane in this case, and the plane of failure. And you can see also very clearly that in these triaxial samples, you get this plane a lot more defined than in the previous one. And there is something also very particular in this sample. I don't know if you can see, but there is a small there is a small streak over here. That's actually natural. I didn't draw that. And that one too. And what that means is that the rock preferentially failed in this condition also as a function of this streak. Because we had axial conditions and symmetric conditions, the rock could have failed in any plane. If you look from the top, it could have been a plane like, now it failed in a plane like this, but it could have failed like there, or there, or there, in any direction. But the weakest direction was the one with this bedding plane. And if you look from the bottom also, that's very clear. That streak over there is that one. All right. So let me turn this off and come back over here. So for this problem then, you just have to analyze this data similar to what you did before, but now this is a triaxial test. And you have a confining pressure which is 1500 psi. Let me see if there is anything else to mention. There is one more thing, and this is asking you to predict what will be the UCS if you knew what the shear strength parameter Q is. And basically what that is asking you is to do an extrapolation if you consider the following case. In this particular test, you have this condition. Your confining pressure is 1500 psi. And if this will be a line 1-to-1, your test starts somewhere over here. Let me do it with red. Starts somewhere over there. And you increase the deviatoric stress of sigma 1 until it fails. And this is actually sigma 1 minus sigma 3 is a deviatoric stress. Until now, everything should be, there is nothing new. The last question of this problem is telling you, if you know that there is a line here with, let me change that to a different slope. If you know that the parameter Q is, what did he say? 5.3, then what will be the UCS? And it's just a geometrical problem. You have a line, straight line, you know its slope, you know that it passes through this point over here, so you should be able to tell me what that UCS is. You can do it, this is just an equation, so you can solve for the unknown value if you know the value of the equation. Let me just improve this plot a little bit. All right.
So how is that Deviatoric stress if it's a constant sigma 3?
Because sigma 1 is increasing. Sigma 1 is increasing here all the time. As we go up, that's a good question. Actually, here this is sigma 1, but this is the peak sigma 1, that particular value. Does it make sense? So
sigma 1 minus initial sigma 1 be deviatoric stress?
yes, so in all these tests, what we do, and what I'm asking in this particular problem, is we increase the deviatoric stress. Usually it starts at 0 or a value close to 0, and then goes to a maximum. This value is the peak. And that value over there is the same that you use over here. So this plot that I just did over here, it is exactly that one with this orange curve. If you add the radial strain will be somewhere over here. I'm not going to add that one, but I'm going to add the volumetric strain. The volumetric strain is going to look something like this. Let me improve it a little bit. All right. So I think you should be able to do this without any problems. If you have questions again, let me know or let Javier know. We'll be glad to help you. I'd like that we go through the last problem. And the last problem includes something that we haven't seen so far. And it is just again a set of triaxial tests. But now we have a pore pressure. In our test in the laboratory, we didn't control pore pressure because we had a dry sample. But in general, in real conditions, rocks are going to be saturated with a fluid. Could be gas, could be oil, could be brine, could be nitrogen, a polymer, could be anything. And to test this under realistic conditions, then we need to control the pore pressure inside the rock with another pump. So we had one pump yesterday. If you wanted to control pore pressure, you will need another pump, and you will need to connect that pore pressure to the rock. But if you do that, then you can control the pore pressure. And in order to calculate effective stresses now, you will have to consider that pore pressure. So when you have a pore pressure, then the effective stresses are going to be the effective radial stress is going to be the confining pressure minus the pore pressure. And the total axial stress or the effective axial stress is going to be the total axial stress minus the pore pressure 2. And let's see what we have in this table over here. So we have confining pressure, pore pressure, and we have peak deviatoric stress. So let me just move this to the side. So then if you have a rock which is saturated, then we have as a variable the confining pressure, the pore pressure, and it could be either the total axial stress S1 if you measure it outside the load frame, or the deviatoric stress S1 minus S3 if you measure it inside. In the problem that we are talking about today, we have this one. All right? So under these saturated conditions, your effective radial stress and minimum stress is going to be the confining pressure minus the pore pressure. Sigma 1 is going to be, same as before, the deviatoric stress plus sigma 3 that you already know from the previous equation, where sigma d is sigma 1 minus sigma 3 but that's also equal to S1 minus S3. Small mistake in here, which is the value that you measure. Notice that S1 minus S3 is equal to sigma 1 minus sigma 3 because both of these have a pore pressure in it. So when you have the pore pressure, it's just you add it and you subtract it, is the same. So at the end of the day, from this data, what you have to do is you have to calculate sigma 3, sigma 1, and once you have those, you put this similar as in the previous problem, sigma 1 as a function of sigma 3. Your data is going to align more or less like this. Let's say that the red points are for pore pressure equal to 0. If you do this correctly, you will see that, let's see what is the next point. So we have 0, 8, and some other values. So let's say that for 8, you have something over here. And I'm going to just make this up, okay? Because you don't have it in your data, but just as an example, let's say that we have 30 MPa. That data should plot somewhere probably over here. It's not going to match exactly into one line, but you should be able to recognize a trend, so that to that trend we do the same that we did before. You feed a line, and from this line you get UCS and the parameter Q. And you're going to observe that regardless of what is the pore pressure, the rock is always going to fail at more or less the same ratio or the same relationship between sigma 1 and sigma 3. And that's very important because that means that rocks do not care that much about what is the value of the total stress. What they care about and what they fail as a function of the effective stress. So you could have, like in an example over here, a super high pore pressure, like 96 MPa, which corresponds to a water depth of about 10 kilometers. So that's quite a big pressure. But the total stresses that you're going to need are quite high too, 130 MPa in this case. In order to fail it, you need an additional 186. But once you subtract the pore pressure, you would see that those values are more or less the same as the ones with a low pore pressure. And in this case, this is another rock that you see something similar. Here it's very similar to that problem in which you have different values of pore pressure, so tests conducted at from 0 to about 110 MPa of pressure with different confining pressures, and you measure what is this value. And you see that those three lines, they have three separate trends. And that's because they are not converting to effective stress. Once you convert all this data to effective stress, all this data nicely lines up into one main trend with all the data, even if though they correspond to different pore pressure, in the same trend. In this particular case, you start to see that at very high effective stress, some of the data may start to deviate from this line. And that's due to other reasons that we're going to see. I'll see if I have time today, but if not, we'll see it on Tuesday. But that's everything you have to do. So the problem number 3 is just the same as the one that you did in the laboratory, that you did in problem number 1, but now you have to add the component of pore pressure. The only thing that you have to do is just to convert these total stresses to effective stresses, and you should find a very nice relationship between the effective stress data. Okay. Again, this is not going to take a lot of time, guys. So I think if we proceed with the exam due to be on Thursday, I want you to do this by Tuesday so that we can upload this on Wednesday morning, the solution, and if you have any questions, then you can check with the solution and you're ready for the exam. I have asked you to do these exercises about calculating Young modulus, calculating these strength parameters. This is what you're going to basically do now. Again, please, do that on your own, even if you share some data with your laboratory mates. That's fine. But this is what I'm going to ask you in the exam, right? I'm not going to ask you to do a regression fit, but probably I'll ask you to draw a line that joins the points or that goes through the main trend of the data, and out of there to calculate either a Young modulus or a Poisson ratio or some of these strength parameters. So you need to know how to deal with this data, how to get from this raw data into the data that you actually need to plot in order to calculate these properties. Or for example, when we go to the case of Young modulus, you need to know how to calculate the strains. If you have initial length and you have change of length, you need to calculate. I might give you a table and you have to calculate that strain and then plot that strain as a function of stress and calculate the Young modulus. I'm going to give you those practice exams so you'll see a little bit more clearly what I expect from you, but it's everything what we have done either in class or in the laboratory. All right, let's see what's next. All right, this is not going to take long, so let's just go through this, and then we'll finish with 4.5. We have seen, let me first come back over here, that at the beginning of the discussion of a failure of rocks, that rocks can fail either in tension, in shear, and this is the last one, that we're going to see, which is in compression. Either failure in tension or in shear are very important because today, thanks to getting to know better geomechanics, we can improve the permeability of rocks by failing them either in tension or in shear. If you create a tensional fracture or a shear fracture on a rock that has a very low permeability, after adding those fractures, you would expect to have a much higher overall permeability. And that's very important because there were reservoirs before that if you were just to put a well and do nothing, they will have a very small flow rate. But if you fracture them, you create fractures in the matrix that help the drainage to be a lot faster. So you're creating an additional permeability that you didn't have before, and that's why geomechanics is so important today, because with unconventional tight reservoirs, without fracturing, you wouldn't be able to produce economically out of these formations. And we're going to see that in hydraulic fracturing, we see both types of failure, tension and shear. Both of them are very important. All right, so while these two types of failures, particularly for hydraulic fracturing and completions and permeability enhancement of tight reservoirs are very important, compression sometimes is not that much, because compression usually what it's going to do is it's going to make the pore space smaller, and it's actually going to decrease the overall permeability of the rock. And let's go, let me show you an example over here. Here you have an example of rock that in this case actually is sand, very angular sand, that this is the condition before loading, and if you apply a significant stress, as you do, for example, when you deplete a reservoir, the total vertical stress stays constant because the weight of everything on top didn't change. You lower the pore pressure, you increase effective stress, you start to compact the rock, but there is going to be a limit, like in this plot is somewhere over here. Here we have axial strain as a function of effective axial stress. There is going to be a point in which if you pass that point, you start to crash the grains. So the grains of the rock are going to start to fail. And just let me zoom in a little bit so you can see a little bit better. So you see in this example how we have very nice pores with a diameter that is about in the order of even 100 micron diameter. But after you go through a very high vertical effective stress, this is going to start to crash, and those big pores are going to get filled now with small grains, and now the pore diameter is going to be a lot smaller. If you remember from petrophysics, permeability is directly proportional to more or less the square of the pore diameter. So if the pore diameter increases 10 times, permeability is going to decrease 100 times. So in general, this is not good. This is not good for permeability, and we're going to see later on that it has some other consequences. Like, for example, sometimes you can have your rock compact so much that the seafloor or the surface on shore is going to start to sink and to go down. That's a phenomenon called subsidence, and can be 1 foot, can be 10 foot, or maybe there are cases in the US where it has been over 40 feet. So it can be quite considerable. And again, we'll see later the applications of this. But in summary, there is going to be a maximum stress at which if you go over that maximum effective stress, you're going to start to fail the rock internally, crushing the grains and making the pores smaller. So in summary, now with a little bit more of understanding about what is going on with the failure of rocks, we can summarize all of that with more circles. And I think that's the beauty of more circles, that they capture all the stresses and all the possible stresses and failures that you can have in a rock. We're still thinking or working in this case in 2 dimensions, but this is also valid for 3 dimensions. Let's start with the first one, tensile strength. You could have compression or no tension on one side of the rock. For example, is on this lateral side is equal to 0. If the stress on one direction gets to the limit of the tensile strength, the rock is going to fail in tension. And your fracture is going to be perpendicular to the applied load. And that kind of makes sense, right? So if you pull in vertical direction, your fracture is going to be horizontal. That's tensile failure. And in order to get there, your Mohr circle has to be very far to the left and into the tension side. If you are somewhere around here where you have compression in both directions, so here you see this is a compression, but one of the compressions is a lot higher than the other one, then we get to cases of that we call anisotropic loading, in which even though if you have compression, one compression is a lot bigger on one direction than in the other. In that case, the diameter of your Mohr circle is big, and you may run into shear failure. And that will be when the state of stress or the Mohr circle meets the shear failure line with this equation. And in that case, we're going to have shear failure. If your effective stresses are so high then that you start crushing some of the grains, then you're going to run into this other line, which is the yield limit for compression. There is going to be a combination of stresses if your maximum stress is too high that you're going to start crushing the pores. And we're not going to see the equation of this line, but it just makes sense that if, for example, we had pure compression, the same in all directions, that would be a circle right over here. And that's going to be the highest compression that the material can resist before going into significant compression strains. If you add some shear to that, and that would mean that the Mohr circle is not going to be a circle right here, but it's going to be like this one, somewhere over here. That means that in addition to a very large compression, also you have a shear on the sample. So your grains are not only going to fail inside the rock by just pure compression, but also compression plus shear. And that's going to make this curve to go a little bit to the left. And what that means is that in this region you have something which is called shear-enhanced compaction, which is compaction but also with the help of shear. Both of them are acting into breaking the rocks and to breaking the grains, and actually that makes it easier. With a little bit of shear, you can make the failure to happen earlier than if you just had pure compression. So we have seen examples of tension and tensile fractures in the lab. We have seen examples of shear failure in the laboratory as well, like this one at relatively small mean stresses. Let me see if I find quickly. I'm missing that in my notes. an example of, well, this is an example of compression failure, the one that I showed before. So this will be mostly pure compression, but I wanted to share with you something which are called shear compaction bands. And this happen in nature too. So all of this failure happens in nature, but some of these are particularly important because let me go with this one. Because if you have these shear-enhanced compaction bands, do you think that that's going to be a good path for enhancing permeability, or it's going to be a barrier for fluids to flow? So will it be a highway for fluid or a barrier? It's actually going to be a barrier. So if you look at this sandstone, probably the permeability of the matrix, it might be high, but when you get to the shear-enhanced compaction bands, that's going to be a barrier to flow. So that's going to block your flow. So in this case, this is not good. All right, guys, work on your homework. Let me know if you have any questions, and I'll see you on Tuesday, and I'll send that email today, and we'll confirm. So as of today, the test is on Thursday, okay? If something extraordinary happens, it might be later on, but I'll let you know. Just prepare for Thursday.